So before we start, Vanessa posted in the chat, Ronald from Lima wanted to mention he made his own 3D printer.
Yeah, hello, Neil.
Hello.
Yeah.
Hello, Niels.
Yep.
This week's work was developing white homemade prints with the result I find in my city firewall in the posted of RepRap.
Oh, that's great.
It's a
From-
homemade printer.
From the city of the Huánuco in was able the collaboration for same work.
Oh, that's wonderful to see. We want to move to Fab Labs making Fab Labs, so it's great to see you making your own printer.
Scam de 4,000 variedades of the potatoes native to Peru.
He scanned potatoes, Neil, potatoes from his city. It's one of the 4,000 potatoes in Peru, and he scanned
Right.
one of them.
Cynthia, in the chat, there's another printer. So yeah, if you haven't been to Peru, Peru has thousands of potatoes, every one that's very different. You know, it makes potatoes in America seem very sad. Nice. Okay, Vanessa and Renal, thank you for sharing that.
Thank you, Neil.
Thank you. Thank you.
So this week's class is for beginners going to be possibly scary, but ultimately very liberating. This is when we start embedded programming. So the assignment is going to be to program the board you made. And I've linked a few interesting examples, but just as inspiration, this was a student who implemented Minecraft this week, which goes well beyond what most of you will do. And how we do this assignment has changed each year. So this year is going to be starting with the board you made and adding an input or an output device and making it communicate. So there's a lot to learn, and it's very important to view this in spirals. You're not going to understand everything to start. To start, we'll give you sample code and you'll make small changes in it. And bit by bit, you'll understand more and more. So the first thing is architecture. What's called the von Neumann architecture came from this report. And there's a lot of interesting history. Most computers like your laptop or desktop use the von Neumann architecture. Harvard came from this project, and in von Neumann, data and programs are in the same memory. So the program can modify its own code, although that's not common. In Harvard, they're separate, that's more efficient. And a famous historical thing is this is a bug in the Harvard computer that was literally a bug. There was a bug that flew in it and it didn't work properly. There's history to that, but it's an early version of a computer bug. So we're going to use the Harvard architecture. Then, let's see. Yeah, Rico has a good description. So from the matrix, there's the red pill and blue pill, and your life will never be the same. CISC is complex instruction set. One instruction does many things. RISC is reduced instruction set, where there's only a small set of instructions, but they execute quickly. And that's pretty much taken over. So we're going to use RISC processors. A microprocessor is in the computer in front of you, there's a processor that's powerful, but it needs separate chips around it for memory and communication and everything else. A microcontroller does less but has more, meaning in the little package is the processor and the memory and the communication and everything. So it's a complete system in a little package. So we're going to use a microcontroller. So Harvard architecture RISC instruction set microcontroller is this week. Beyond it, there's many things. There's multi-core processors, there's graphical processors, there's programmable logic, there's software to design chips from scratch. And this is research I'm doing in my lab about new geometry, new ways to think about computing as geometry. We're not going to use those, but this is just to look further ahead. Now, one of the main processors we'll be using, the brains of the system, is this one, the AT-SAMD11C. The SAMD11C, that's the part, cost about $1. And for this week, one of the group assignments is to browse the data sheet. Here's the data sheet. For the $1 part, it's 1,000 pages long. There's a whole universe in this. Each section here is one subsystem. So if we get to this picture, this shows you what's going on in that $1 part. There's a whole universe. There's the processor that actually thinks. This is memory and the memory controller. This manages communication on the chip. This talks to USB. This is how we're going to load code. This talks out to the pins. And then all of these are peripherals, and we're going to spend many weeks learning about them. They do inputs, outputs, manage time, manage events. And so this isn't just a thing. It's a whole world. There's a whole universe in there we're going to be taking time to learn. So one thing in there is the memory. So there's registers, which is where the processor can operate, and those go quickly. There, depending on the system, there's SRAM, which is static RAM, which is faster general purpose memory. There's DRAM, which is slower but larger for larger capacity storage. There's EEPROM, which is memory that stores information when you turn the power off, and that's easy to reprogram. There's flash, which is memory that also stores information without power. It's harder to program, but it's has more capacity. And then there's fuse, which is memory cells that set the configuration of the processor. So there's many kinds of memory. Then there's many kinds of peripherals. This is how the processor talks to the world around it. So ports send data out on pins and get data in. A to D takes an analog voltage from a sensor, for example, and turns it into digital data. A comparator just compares two voltages, which seems less useful than the A to D, but you can do it much faster. D to A goes from digital to analog, so it lets you make analog signals. These are really handy modules. These measure the time of events, they count events, and they can do something that might not seem very important to start. They can make pulses where you vary the width of the pulse. And that's going to turn out to be essential for making sound and controlling motors and doing all of the kinds of interfacing we want to do. USART and USBs are modules that communicate. There can be modules that do math to speed that up, modules that do cryptography to make operations secure, and there's still many more other kinds. So these are all separate subsystems you'll be learning about. The word size is how much information a processor can operate at the same time. So the simplest, cheapest processors we're using are 8-bit. The more powerful ones we use are 32 bits. And then the computers around you typically are 64 bits. But bigger isn't always better. The 8-bit processor can operate on 64-bit data. It just takes a few instructions. But in return for that, everything is can be faster, better, cheaper. The 8-bit processor can cost less, use fewer transistors, can use less power. And so we'll see many powerful things you can do with very small processors, as well as options for the bigger ones. So there are a number of families of processors we'll be using. This is a page I keep of a benchmark where what I'm doing there is I have the processor. I send out on a pin a high-level signal. I then read that back in. I then invert it in software, and I put that back out. And so what that makes is a waveform that oscillates, and it measures the round-trip time to go to the outside world and back in again. And if you look at this list in millions of cycles per second, it goes from 0.02 to 60 as we vary the architecture and the programming language. And the very same chip, you'll see at many different places based on which programming language we use. So over time, we'll learn about why there's this range. And then this table is doing a very simple calculation. It's calculating pi by summing a series. And this one is an even bigger range. This is in billions of operations per second. And it goes from 0.0000001 up to 17 million. So it's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros from the slowest example to the fastest example. Now, the extremes of this we won't do in this class. At the top, this is one of the world's biggest computers, but in the middle here are speed ratings for many different processors we're using, and the same processor for many different languages. So in the coming weeks, we'll be learning about why there's this widespread in them. So to tour through the families, this at the bottom is a processor, a very simple processor just made out of cardboard, a mechanical computer. This is a crazy project. This weighs a few tons, and it has the same power as our little $1 processor, but he was interested in how they work, so he made a room-sized version, one transistor at a time, to learn about it. I love this project. The 6502 is a very important integrated circuit, and this was somebody who made a printed circuit board, and he placed each transistor individually, so there's no traditional chip fab, and he made a whole microprocessor as just a circuit board. And those are just pedagogical, interesting examples. 8051 is an ancient processor, still around. I don't recommend for anything. PICs and MSPs have a long history. We're not going to focus on them. The ones we care about, one is the AVRs. So AVRs came originally from a thesis of two Norwegian students, and they wanted to make a processor that could use modern languages. So these are 8-bit processors. What's nice is they come down to tiny packages. So this version is about the size of a grain of rice, and is 30 cents in quantity. One size bigger is, this is a favorite. This is the 412. It's a modern processor, modern architecture, 50 cents in quantity in a simple 8-pin package. And that's a really handy one for when you need to paste in just a little bit of processing locally. This is a slightly bigger package, and this is somewhat more powerful inside. It has it uses the same instructions, but it has more powerful peripherals. And then this is one in a bigger package still, and this has really interesting analog logic for measuring things like low-level signals. So these are 8-pin processors, very convenient, modern programming tools. So that's one family we use. Then ARM is a British company with an interesting history. They don't make chips. They just design the core design of the chip, and then many other people customize and produce them. And so one family we make a lot of use of comes from Microchip, and it's the SAMD family. And this goes from the D11 is the one I mentioned that comes in the 14-pin package, a bit over $1. And it is 32 bits. It has built-in USB to make USB peripherals. It's a faster clock speed. And that family goes up to the D51, is a much bigger one to provide many more pins. These are more powerful. They're harder to use. And so the AVRs you can program at a fairly low level. These processors, you need to use libraries that help you with them. But in return for that, it's a fast processor with powerful peripherals. And then you can get more of everything, more memory, more kinds of resources. So that's the SAMD family. STM has a popular ARM family. Then this is one of our favorites. The people behind the Raspberry Pi developed their own custom processor called the RP2040. This is one of the nicest data sheets. Many data sheets are hard to read. This data sheet is beautifully written. The RP2040 is faster still. It's 20 operations per second for the AVR, 48 megahertz for the SAMD. The RP2040 normally runs at 133, but you can overclock it, and it's run it faster than it's spec'd for, and it's reliable at, say, 250 megahertz. It has more memory. And then one nice thing is, excuse me, it has 2 processing cores that can run independently. And then, let's see, Ricardo's, that's an RP2040 at a gigahertz. That will literally melt it, not metaphorically, but literally melt it. So to do that, you have to cool it cryogenically. It's a crazy fringe. And then one of the things that's best about the RP2040 is it has, around the main processors, it has a bunch of little tiny processors that each run a very efficient low-level code, and they let you program in software peripherals. And you'll see a number of examples I'll show you of using that to customize the processor. Now, faster isn't always better. Faster uses more power. All of these let you slow the clock down if you don't need the processing speed to save power, for example, for a battery or a solar cell, but you still get the advantage of the architecture. So there's a kind of natural flow from the AVRs to the SAMDs to the RP2040 in moving up in processors that have more power, but also more pins, more complexity, costs more. Extensa has a history that comes from what's called MIPS. That's used in ESP 8266 and 32, which come from our friends in Shenzhen, and those integrate radios. And so we'll use those to do Wi-Fi and Bluetooth. RISC-V is rapidly changing this whole landscape. So ARM charges a lot in licensing fees. RISC-V is an open family. It's an open standard where you don't have to pay to license it. And so many processors are now being developed around the open RISC-V family. And the ESP32C3 is an important one we're going to be using to do, it's a fast processor with modern tools, with radios, again, for things like Bluetooth and Wi-Fi based on RISC-V. Let's see, Stephen in the chat has posted a fun thing, which is, it's a Where's Waldo? It's find the tiny 10 on that little board. Okay, so, and then beyond that, these are all more specialized processors that are different because they have many cores when you need more embedded performance. And yeah, Nicholas is noting underclocking. It's an interesting exercise. As you, I'll talk about power measurement when we get to output devices. When you reduce the power, when you reduce the clock speed, you can see the power come back down. Now, one issue is with these processors, there's always a problem, which is if you look at the production of them and the demand for them, they're always disconnected. So demand goes up, manufacturer starts making more, the economy slows down, and the manufacturers have too many, so they start making less. And then in here, it's coming back up. You want more of them, but the manufacturer's making less of them. So frustratingly, these go in and out of stock. And so one site we use is Octopart, is a search engine for parts. So if we look at ATtiny44A, this is one of the 8-bit processors, and this shows you all the versions you can get it in. So this is the surface mount. That's the one we'll be using. This is a wafer scale package where you essentially take the die and just package around it. So this is smaller, but it's trickier to solder. This is a through-hole version that we won't be using. Those are almost obsolete now. And then this shows you which vendors have them in stock and how much they have in stock. Like if we take this example, this is the tiniest package. And here there's a few there, and some of the other vendors, they're out of stock there. On the other hand, this package, there's lots of them. And so that's an example of how it comes and goes. DigiKey, Mouser, Newark, Farnell are all vendors we make a lot of use of for them. And then SparkFront and Adafruit, we don't use for the basic just purchasing chips, but we do use, they make all sorts of development boards around them and parts we use with them. Let's see, Francisco posted a link to a Microsoft simulator in Excel. That's a bizarre combination. So in the packages, dual inline we don't use anymore. That's through hole. These are all surface mount packages we'll be making a lot of use of. And then these are the tiniest packages. We won't generally use those for processors. We will use them for some special sensors, but this shows BGA is a ball grid array. And so it's where the processor has many small balls under it. And so this actually shows using the milling process we're doing, but with a carefully calibrated mill with everything in good condition, and actually mounting a BGA package. And this is beyond what most of you will do, but showing that it's possible. But we'll be using these surface mount packages. Okay, so you've picked out a processor. You've picked out a package. Now you need to program it. And the most important tip is nobody does this from scratch. As a beginner, we'll give you sample code and you'll modify it. But even as an expert, I never write an embedded program starting from a clean sheet of paper or a clean editor. I always take something I've written or another example and build on it and change it. So don't be alarmed if you don't understand everything in the programs yet. Start with the examples we'll give you and start modifying them, and slowly you'll understand more. So there's multiple levels of programming. At the bottom is this. This is a hex code. This is what actually goes in the processor. You could write that by hand, but nobody does. But what that's doing is the processors have instruction sets. So this is the instruction set for the AVR. And this is the code to add two numbers. And then when you add two numbers, these are the registers it uses. So that's in physically what the processor understands. Now, one level up from that is what's called assembly language, where instead of writing numbers, you write words, but each word is an instruction from the instruction set. And in the old days, that's how we used to program. It's almost never done now. However, you can do what's called inline assembly language, where you write a higher level program, and in your high level program, you put in a few assembly language instructions. And the reason why this still gets done is this is the fastest and most efficient. And if you really are doing things that are critical in time, occasionally you descend down to that level. Now, one of the nice things about the RP2040 processor is it has little processors around it designed to be programmed in an assembly language, in effect. And so that's a place where you can still do it. Leo is asking about assembly for critical components. No, I'm going to talk about that in a little bit. But other than these specialized purposes, you won't see assembly language. It was sad for me when we stopped teaching it. It's come back a little bit in the RP2040. So then comes C. C is a venerable language from Bell Labs that's a bit higher level than assembly language. And let's see. So this is an example of a C language. So this is the main routine. Here I'm giving names to some variables. And then this is making a loop, and I'm going to execute some instructions. C has one of the oldest higher level languages. C++ extends C with objects, so you can define both types of data and how to operate on them. This is a recitation on just the structure of programming to learn about programming. This talks about the types of data. And C is the most common language used for embedded programming. So GCC is a very important open source project for compilers that runs down to the smallest processors. So GCC takes your C program, where you say things like, I want to make a loop, and turns that into those low-level instructions that the processor understands. And GCC is used from tiny processors up to supercomputers. You can use it directly. These are libraries to use it with AVR. These are libraries to use it with ARM. Microchip makes tools to use it. You won't see it directly, most likely. I'll show you how to use it directly. Most of you will use it behind Arduino that we'll talk about in a few minutes. Now, C has been around forever, and it's easy in C to make security mistakes. So you can define a variable, but you can have what's called a buffer overrun, where it goes into a space it wasn't supposed to be in. And by doing that, you can get access to data that you shouldn't see. And so many different security vulnerabilities that have been used by hackers to attack systems come from mistakes you can make in C. So Rust and Go are more recent languages that prevent that. They prevent what are called memory leaks, where your program loses memory as it runs. They prevent overruns, where you can access places you shouldn't be. They prevent race conditions, where two things happen and the order that they happen in isn't defined. And in fact, just in the last few days, the White House in the US, the government, issued a policy statement asking people to try to move from C to these languages to reduce the risk of hackers. So initially, these started for things like critical core software. So there was a question about moonlanders. Hank put in the chat the White House report on this migration to more recent languages. These were developed for critical conditions, mission critical servers for business, for society, for everything. But these have now been ported to embedded systems. And so if you go back to one of the featured assignments, this one, and again, this was done in a version of the class where we didn't make circuit boards first, which is why you see the breadboard. You won't be doing that. But he did Minecraft in Rust, and so he talks about how he used Rust for that. So most of what you'll see in the examples in the class and in tutorials and libraries will still be based on C, but Rust and Go are increasing and are good things to learn for the future. Then come interpreters. So Python is a beautiful language, and I'll come back and talk more about Python in go ahead to this week is where we'll be building desktop programs. Python is a beautiful language with interesting history. It's interpreted. So C is compiled. You write the program and it gets turned into instructions for the processor. Python is interpreted, which is you write the high-level language and the interpreter, one line at a time, turns that into an instruction for the processor. That's very convenient because it's more interactive, but it's slower. And if you go back to the benchmarks, you'll see there's a big difference in the speed between doing things in C and in Python. But in return for that, Python is interactive. You don't just write a program and run it, you can interact with the program. And there are a number of ways you can improve the accelerate Python. And there are two related, very important ports now of Python for embedded systems. So MicroPython and then CircuitPython from Adafruit forked off from MicroPython, and it focused on extending the hardware interfaces. Both are powerful. I recommend both. I've used both. I currently do a bit more with MicroPython, but both are recommended. And the more powerful processors we're using, like the ESP32 and the RP2040, those are fast enough that you can feasibly use them in Python. And you have the best of both worlds in the RP2040 because you can use Python for the high-level program, but you can program the little peripherals around it with the low-level language. So Python is beautifully documented. In it, the REPL is the read, evaluate, print loop where you type commands and it responds to you. This is a link to ways to speed up MicroPython. And then this is a project Quentin, one of the instructors, did to build a bridge between the embedded Python and the high-level Python. So I'll be showing you examples in both Python and C. These are embedded versions of JavaScript. They do exist. They're much less active than the MicroPython. And so I recommend progressing from C to the embedded Python for your language. And let's see, yeah, in a little bit, let me not do that now. I'll be going through these examples to show you sample code. Okay, so you have to pick a architecture, a processor family, a processor in the family, and a package to use it. Then you have to pick the language you'll be using. Then the next thing that comes is in-system development. So you have a circuit board. Let's see, you have a circuit board and it has the processor in it. And in the old days, you actually had to put the code in the processor, then put the processor in the circuit board. Now we don't need to do that. You can change the program while it's in the circuit board. So that's called in-system development. And there are many ways to do that. So you can physically connect to the processor and use its protocol to load it. So the AVR processors use what's called UPDI, and that has a 1 pin in the circuit. So if we go down to in the tiny 412, this pin labeled UPDI, that's the pin you load the program in on. It uses a simple serial communication protocol. For the ARM processors that we're using, it uses what's called SWD. And SWD is a few more pins. So if we come back down here, let's see. Let me find. Let's go to the picture. Here's a ARM processor. Here's a USB interface, and then it has these 4 pads. And those pads are to load a, let's see, if we go to that, those pads are to load an SWD program. Now, one of the neat things is if you made the Quentoris in Electronics Production Week, the Quentoris has the processor. It's got an LED and a button. And so the LED lets you see when you turn on a pin out. and it's got a button that lets you read a signal in. And then it's got two other things. It's got a serial port, and you can use that for UPDI programming. And it's got an SWD port, and you can use that for ARM programming. So the Quintaurus you made, and it also has these pins that you can use on a breadboard or with wires to connect to things off of it. So it lets you experiment with signals out, signals in, and interfacing, but it is also a programmer that lets you program the other processors we're using. So if you made the Quintaurus, you already have SWD and UPDI programmers. Then bootloaders are programs that load programs. And so with SWD or UPDI, you need a programmer to load the program in. But there's a very special kind of program. So this is the memory space of your processor. And normally you take this programming interface and you externally load, and it fills the memory with your program. But remember, these processors can communicate. So they have communication ports like USB. This is the programming port. There's a very special program you can load that stays in a certain part of the memory called a bootloader. And that's a program to load programs. So once you load the bootloader, then you no longer need the programmer, because what the bootloader knows how to do is listen to the USB and over the communication port, load a program. So bootloader takes up some space, but in return for that, you don't need a programmer anymore. It's a program to load programs. And so for the smallest processors, we don't use bootloaders because space is a problem. But for anything bigger than that, the first thing we do is we use the programmer to put in a bootloader, and then we just use a communication interface to load programs in the future. Now, if you're using Python, instead, REPL is where you type commands to it, and it types commands back to you. And I'll show you examples of that. You can do that over a interface like USB. And in fact, if you have a Python processor with a radio, you can actually program it over the web. You can actually use a web interface to change the program in it. If you just type the program, it'll run. But in MicroPython, when you turn it on, it first runs a program called bootpy. And then if you save a program called main.py, it'll run that automatically. So you can run programs in Python with the interpreter, or you can save them and they run the next time you turn it on. So there's no notion of the programmer needed. You're just using this interface to load the code into it. So that's how we're going to get program into our processor. Then you need to write the program. A tool chain is all of the steps to go from your program to loading it. So you have to turn your high-level program into low-level codes, and then you need to get it into the processor. Microchip that makes AVRs and SAMDs, they have Microchip Studio, which is their program to do it. Eclipse and VS Code are open frameworks for editing designed for coding. And VS Code has become very popular as a cross-platform programming tool that lets you write code, but it has all sorts of supporting tools to help you with the process. Thani is an easy-to-use environment for writing and running Python code. Platform.io is kind of a universal web wrapper around many different architectures and many programming environments. And then we get to Arduino. So just the word Arduino is a subject of great confusion. Arduino has 6 meanings that are all separate. So Arduino, you might know as the boards that look like that. So an Arduino is used to refer to a board. When you install the Arduino environment, you see the software from Arduino, but under the hood, underneath it, it brings with it the toolchain. And so one of the most useful things Arduino does, it's an easy way to install the toolchain. So if you want to, so any of the processors we're using, you can use the Arduino environment for. And installing Arduino is a really convenient way to install the toolchain rather than having to do all the separate steps. When you write in the Arduino environment, you're actually writing C code. It's actually C++ code. And it uses libraries. The Arduino libraries aim to make it easier. So they're not specific to the processor. They work on many different processors, which is convenient. On the other hand, they can be inefficient and they can prevent you from getting access to parts of the processor. Arduino is a user interface. The IDE is the integrated development environment. There's an Arduino bootloader you can use for bootloading. And Arduino headers are the particular geometry of the plug-in boards. So when people say Arduino, they can mean each of these things, but each of these are separable. So you can use the Arduino toolchain to program the processors we're using while skipping all of the other steps. You can use the Arduino toolchain, but not the Arduino editor to use a more powerful editor. You can mix and match each of these elements. This is a nice page that explains how what's called the Arduino sketch, which is just C code, but with libraries turns into the executable. And then these are some extensions of building other interfaces on top of alternatives to the Arduino IDE. Now, the original Arduino used the 328P processor. And you might still see mention of that, but that processor is many generations obsolete. It shouldn't be used for anything anymore. But post that, what Arduino did was develop the notion of cores. And what a core does is take your general purpose Arduino program and specialize it to processors. So this is an Arduino core for the RP2040. This is one for the ESP32. This is the 8266. This is an important one. This is for the SAMD processors, and it wasn't being well maintained. So Quentin, one of the instructors, did a fork of that and maintains that for us. This is one for the AVRs, and that's done by a colleague who happens to live in Cambridge. So, and we'll see this in a little bit. When you use the Arduino IDE, you use a core to specialize it for a processor. Now, there's a big overhead in performance. Arduino's libraries are much slower than low-level hardware interface. And so on this page of benchmarks, you can see that performance comparison. Next comes development boards. Take the processor, they add connectors to get off of the board, and are used for developing code. Shells are one of our favorites. Seed Studio is a good friend of the lab, what we do. And these shells are a neat form factor. It's the processor in a slightly larger package with the things you need to program it and the USB interface. And this whole thing acts like a processor you can embed in your board. So we're going to make a lot of use of shells. And then this is a number of different generations of development boards. And most recently, the Quentaurus is the one we're recommending. Okay. Operating systems run on top of your code. So far, what I've described is what's called bare metal programming, where you just write your program and it runs. Once you have a processor doing many things at once, you then need an operating system. And so simple multitasking, doing more than one thing at once, you can do in MicroPython with what's called cooperative multitasking. Once you need to do multiple tasks at the same time, so the computer in front of you is doing Zoom and web browsing and reading your email and minding the clock and all of that, then you need an operating system. These are operating systems you can use as the processors get larger, but later I'll talk about an alternative, which is to make multi-processor systems. So we won't talk much about that. The processors have clocks to tell time. And as I noted before, you can slow it down to save power, or you can make it run faster, which can go out of spec, but can be safe and can increase performance. Then we need to communicate. So for this week's assignment, we wanted to interact. And if all you have is the LED and button, you can blink the LED at, under the program, and you can have the program read the button. And then we wanted to communicate to send messages. So like when you push the button, it sends a message out, or when you send a message in, it controls the LED. To do that, we need to communicate. So RS-232 is an ancient standard for wiggling signals to communicate. And then you use serial terminals to talk to it. So the Arduino IDE has a serial monitor that lets you send messages in and out. In Linux or Mac terminal, you can use a program called Screen. If you install Python, you can use Miniterm. In JavaScript, you can use serial port. In a web browser, you can use web serial. I'll show you examples of all of these. And USB can do many things, but the simplest thing USB can do is just carry serial. So with the SAMD or the shells, you plug it into a USB port, it becomes serial, and you use a terminal to communicate. So now let's do examples. So this is a board, and on the board all I have is a shell, and this is the C3 that has a radio, and I have a button and an LED. And then this is an Arduino program. So INO is an Arduino program, and it's a C program with the Arduino libraries. You have to set the setup, gets the processor ready to run. You have to tell a pin, is it an input or output? So here I'm saying the LED is going to send a signal out, the button is going to take a signal in, and I'm going to communicate over the serial port. And then loop keeps running. So this says, if I've got serial data, write to the pin and read what I sent and send it back. And then this reads the button and sends a message out. So that's a Python program. Then, sorry, that's a C program for Arduino. Then this is a Python program. And so in the Python program, you bring in libraries. So these are some libraries I need to talk to. This sets up the pin out. This is the pin in. Here's my loop. And I check to see, do I have data to read? And do I have something to do with the button? So now let's look at a video. So here's my RP2040. It has two buttons. One is to reset it, and one is to go into its bootloader mode. The bootloader mode is to reset it to load new programs. So what I'm going to do first is I'm going to reset it, the bootloader. I'm going to tell Arduino to connect to the port. Then Arduino recognizes it and figures out how to load the code. Runs, it's still flashing it. Once I've done that, the port just changed. Because it loaded the bootloader code, the USB moved to a new location. So I have to reconnect to that. And now I can run my program. So I push the button, the light blinks, and I get a message. And down here in the serial monitor, I can type messages, and it types back to me, and the light blinks. Now I'm going to do the same thing in Python. So that was in the Arduino IDE. Now I'm in Thani. I'm going to reset the processor while holding the boot button. And so I need to reboot load it. And so now I've reset it. Then in Thani, I find the port, and I'm going to install MicroPython. So it just put all of MicroPython on it. Same thing, I now need to move to where the port is. And so now in what you're seeing, up here is the program, down here is the REPL, the command prompt. And so in that command prompt, like I just typed 1 + 1 and it told me 2. I'm sending commands to it, it's executing them and coming back. And now I'm going to run my Python program. And now it does the same thing. I push the button, I get a message, I can come here, I can type, and it types back to me and it blinks the LED. So all of that was for the RP2040 loading a program and running it. The Pico is the same processor, just in a package with more pins. And so it's very inexpensive still, $4. But you can use that if you need more pins. And here's a crazy project. This is a port of the video game Doom to run on the RP2040. So very powerful processor, easy to use. And in coming weeks, we're going to do much more on how we use it to program its high-speed peripherals to do all sorts of things. The RP2040 has two main processors. And so this example has a loop and a loop 1. And here I'm putting, in the Arduino environment, code on each processor. And then in the Python version, what I'm doing is multi-threading. And so this is halfway to an operating system. What I'm defining are two separate processes, one doing communication and one talking to the button. And they're running separately at the same time, doing multitasking. Excuse me. So that's the RP2040. The C3 is the Xiao in a similar package. And this one is nice if you want a radio. And so here I've got the C version, the Arduino version. Again, I've got the Python version. And then this one is slightly different. So I'll start by resetting it. in the Arduino environment, I need to tell it the core that I'm using. Then I need to go to the port, and I can load the code and blink the LED. So this is the same as the RP2040 example. Then, so let's see, I'll answer that in a second, Ricardo. Here, I'm going to do it in Python. In this case, you have to manually load the Python interpreter. And so for this processor, Espressif provides a tool to load the code. Ricardo is asking about the bootloader. Ricardo, the Arduino loads the bootloader. Once I only reset it to change the code the first time. Once you've reset the processor and run the Arduino IDE, it's loaded the bootloader and you don't have to push the button again. So now I'm using the tool from Espressif in a command line to load the Python interpreter, because that wasn't yet built into Thani. And now in Thani, I can do the same thing. I can tell it the port that I'm on. And I can run my program and I can blink the light and get messages in and out. Okay, so that's programming the ESP32. And in coming weeks, I'll show it talking to phones and the web. Now let's go to the SAMDs. So this is a SAMD. So this is a level below the shalls. The shall, in fact, let me go to, oh, sorry, I think, let's see, I guess it's not on this page. Yeah, what I wanted to find was, let me take a minute to show you this. Let's go to here, and then go to here, and then go to here. So this is a X-ray microscope in my lab, a micro CT. This is a shell, and then this is showing you what's inside the shell. So the reason I wanted to show that was down here, working with the chip is one level below the shell. It's the bare processor, and you make the parts around it. So in this case, on this board, we have a USB interface, the LED to blink, and then USB is providing 5 volts. This is a regulator we use to bring it down to 3 volts. And so once you've done that, then what I'm showing here is 2 different ways to program it. First, what I'm doing is the very lowest level, which is I'm not using Arduino at all. I'm just writing my own C program, and I'm using the tool chain to load the workflow. And eventually, you might, depending on what you're doing, grow out of the limits of the Arduino environment and just do it at that level. Let's see. Luis is asking about Xiao and QTPY from Adafruit. They're very similar. The reason we use I prefer the shalls is the Adafruits, the one I'm aware of, have parts underneath, so you can't surface mount them without making holes in the board. The shalls are designed to be surface mounted. So I just blinked the LED from C directly. Now I'm doing the same thing from the Arduino IDE. So I'm telling it to use the core and load the bootloader, and then I can run the program and blink the LED. So using the AVRs, they're cheaper than the shalls, smaller, and if all you need is a bit of processing, it makes sense to use them. And so this is an example showing blinking an LED, sending messages in and out. And then this is going up to, this is a bigger SAMD, same instruction set, same programming, just more pins. And so if you grow out of pins on the SHAO, you can go up to the Pico, but you can also go up to the SAMD 21 if you just need more pins for your project. Then you might get through this class and never use this, but this is the Tiny 412. And so it's a powerful little processor. And so here I'm showing programming it in C and again, programming it in the Arduino IDE. And there are all sorts of use cases where you're making like a big distributed system and you just want to paste in a little bit of processing. And so this is much smaller and cheaper than the SHAO. But again, you can use the full Arduino IDE as the development environment for it. It's too small to run Python, but it's happy to run C code or emerging Rust and Go. So that's programming the Tiny 412. And then this is going up through the AVR family. Yeah, and then Ricard has noted Arduino is an interface into the toolchain. VS Code is a more powerful editor. Platform IO is one level above Arduino. It's a wrapper around Arduino and many other different environments. So personally, I don't use much of Arduino libraries or development tools, but I rely on Arduino because it's a very convenient packaging of the toolchain. It's just a very easy way to install the toolchain, whatever other tools you use. Okay, two final topics, very important. When this is a recitation on debugging, when you make your circuits, they often won't work. And so this is a checklist of standard things. Check your solder joints, make sure components are in the right orientation, check the data sheet, make sure connectors are the right way, check the voltages, make sure they're coming in. If that doesn't work, look at the input-output signals. In software, you can blink an LED to send messages. You can send text messages. And very recently, this is hot off the press, the programmer you made can talk to real-time debuggers. So this is the programmer. This is a target board. The new version of Arduino knows how to talk to that for in-circuit debugging. So Quentin is going to run this program. It's going to load the program. He's doing it without a bootloader to save space. Now what he's going to do is he's going to go to the debugger tab. He's going to put in what's called a breakpoint, and that stops the execution. He runs the program. It stops at the breakpoint. At that point, you can check all the variables in your program. You can read and what it's doing, modify it, and restart it. So it lets you stop and start and probe the program, which is very powerful for figuring out what's going on with it. Leo's asking about STM32. STM32 and SAMDs are fairly equivalent in the range of what they cover. They're very tiny relative strengths and weaknesses. We like the SAMD for the tool chain support for the range of families, but it's almost a coin flip between the SAMD and the STM family. They're very, very similar. Okay, last topic is AI. These links are TensorFlow Lite, TinyML. This is for Espressif, and then Edge Impulse. These are all environments to do embedded machine learning, where you can train a machine learning model and run it in your processor. So rather than tell it to recognize a gesture by figuring out how to write the program, you train the machine learning model. And then ChatGPT is a general purpose conversational agent that can write code, and Copilot is a specialized conversational agent for writing code. These can write code for you. The issue is they can do crazy things. Let's see. So this, let me remember what it did here. This is writing, okay. So this is asking it to write code. Now I'm going to ask it to blink an LED on a SAMD11C. And now it's happily writing the Python code to run on the SAMD. The only detail is MicroPython doesn't run on the SAMD 11. It doesn't remotely fit. So everything it just showed you, the first part was exactly right. The second part was almost right, other than it doesn't work. So you need to be very careful. The AI environments can write correct code, but they can introduce bugs. They can make up things when they're not sure, and they can also infringe copyright. So try them, but it doesn't replace understanding what they're doing. And it's very important that when you use AI tools, you need to credit all of your sources, and AI tools are a source. So wrapping up, this is Quentin's programming assignment. This is Adrian's programming assignment. Both did a great job doing it and documenting it. This is this more recent example of RP2040 with Russ doing Minecraft. As a group, work through the data sheet. And as a group, I'd like you to compare different development environments, different types of processors. For you individually, take your dev board that you made. I want it to be one you made. Make it do something local. Read a button, blink an LED. You could use the off-board connectors to add other sensors or actuators we'll be talking about. And then send a message. Simplest is a serial USB message. If you want to get ambitious, you could start using radios. And then extra credit is you can experiment with other languages and other development environments, like compare C versus Python. And then other extra credit is you can add some off-board components. We're going to spend a week just on inputs, a week just on outputs, but you can start experimenting with adding external components to the boards. So this is a lot to learn. The main thing I want you to take away, so this is a very empowering class, as Rico shared the red pill versus the blue pill. Nothing will be the same once you make this entry into the world of embedded programming. The main lesson for today is don't worry, be happy. Don't start from scratch. Start from code examples, get the code examples running, and then begin to change them. And then I'd say the other really important lesson is what's so tricky about the debugging is, let's say you just want to read the button into the processor and have it control the LED. If it doesn't work, the mistake might be in your program. It might be in how you loaded the program. It might be in the connection of the processor to the board. It might be other components on the board. It might be in the power supply. The mistakes, the faults can be in hardware, they can be in software, or they can be right at the boundary. And so in coming weeks, we'll be learning more about how you probe and debug these. But it's more than just software or just hardware debugging. And that's something you'll be getting lots of experience on. So looking ahead, Hank and Nicholas did a nice recitation helping you get started on programming and debugging. Their slides and video is linked. No recitation in the coming week, but the Saturday open time will be very important to help you get started. And the real goal this week is to get the tool chains installed and get code going into and out of your processors. And then we'll spend many, many weeks unpacking everything we did into more and more detail. Okay. Any final questions or comments? If not, welcome to the wide world of embedded programming. And this is where the magic of the class comes in. All the different ways I say you can do that really comes from what we can do with these processors connected to everything else we're learning. So I'd say we're back to 3D printing was one of the most expressive weeks. We're back to this is one of the least expressive weeks. The programs you make likely won't be all that interesting, but what'll be interesting is getting you started with the tool chains and starting to think about how you use this in your projects. Happy programming. See you all next Wednesday. Bye-bye.
Ciao, ciao.
Tack för ikväll.
Ciao, ciao.
Eso.
Vemos. Ciao, ciao.
Ciao.
Ciao, ciao.